Hello everyone, welcome back to School Education NVK YouTube channel. Today we are delving into the fascinating world of linear algebra to explore a fundamental concept, the spanning set theorem. I am excited to break it down for you, so let's get started. First, let's see an example to understand the concept clearly. First, let's take a vector space, which means it consists of a set of vectors. Here, vector space means it consists set of vectors. Let's take v1, v2, v3 into a vector space. I am representing vector space v. Let a belongs to v, which means a is equal to v. Here see, I wrote v1 is equal to 1 0 0, v2 equal to 0 1 0, v3 equal to 0 0 1 vectors. Okay, just I added all three. Here see, then just I took 1 as a scalar, which results none. Then I wrote c1 v1 into plus c2 v2 plus c3 v3. Here span means writing linear combination. Here the vectors are v1, v2, v3. Span means writing linear combination with vectors. c1 v1 plus c2 v2 plus c3 v3 is a linear combination of set of vectors v1 v2 v3. Okay, so I wrote span of v1 v2 v3, span of v1 v2 v3. Okay, here span of v1 v2 v3 gives complete vector. See in previous steps, c1 v1 v2 c3 v3, then 1 1 0 0 plus 1 0 1 0 plus 1 0 0 1, which means 1 0 0 0 1 0 0 0 1. It is a complete vector space. So span means it gives a complete vector space. Span of v1 v2 v3 gives a complete vector space A. So I represented A is equal to span of v1 v2 v3. Okay, here span nothing but linear combination, just a linear combination. Here v1 v2 v3 are independent vectors, which means we cannot bring here v3 using v1 and v2 and v2 using v1 and so on. So these are the independent vectors. Let's enter into a theorem. Spanning set theorem. First, let's read statement. Let S is equal to v1. Let S is equal to v1 v2 up to vp. Here we took set S is equal to v1 v2 up to vp. These all are the vectors. We wrote all vectors in a set S. Be a set in V. Here V means vector space. In a vector space, we have a set of vectors v1 v2 up to vp, and H is equal to span of v1 v2 v3 up to vp, means linear combination of v1 v2 up to vp, we get a vector space V, which is represented by H. Next statement 1. If one of the vectors in S, say vk, is a linear combination of remaining vectors in S. Suppose we wrote vk as a linear combination of remaining preceding vectors up to vk minus 1. Then the set formed from S by removing vk still spans H. Here they are saying that we have a set v1 v2 up to vp. Let's assume v1 v2 up to vk. For example, if you wrote vk is equal to c1 v1 plus c2 v2 plus up to ck minus 1 vk minus 1 up to a preceding vector, then the linear combination of remaining vectors in S, then the set formed from S after removing vk still spans H, means after removing vk minus 1 also, vk also, we get a vector space V. Just now we assumed that using v1 v2 up to vk we get a vector space which is H. Although if we remove vk also up to v1 v2 up to vk minus 1 also, we get a vector space V. Next statement 2. If H does not equal to 0, which means H is not a null set, means it at least one vector, some subset of S. it is some subset, is a basis for H. Let's see to understand it clearly. Proof. Statement 1. Let S is equal to V1 V2 up to Vp. Here S is a set. Be a set in V vector space where V1 V2 up to Vp are vectors in S. These V1 V2 Vp are the vectors. Okay, these V1 V2 V3 are the vectors. I wrote H is equal to span of V1 V2 up to Vp using the vectors V1 V2 up to Vp. If you write it as a linear combination, span means linear combination of V1 V2 up to Vp, we get a vector space V. It is represented by H. We may use directly V also, but for our convenience use H. H belongs to V, or H is equal to V. So H is equal to span of V1 V2 up to Vp. If Vp be a linear combination of vectors V1 V2 up to Vp minus 1, so linear combination of preceding vectors, just preceding vectors, then I wrote Vp is equal to A1 V1 plus A2 V2 plus up to so on A P minus 1 V P minus 1. Here A1 A2 A P minus 1 are scalars which may be 1 2 or etc. so on. Here V1 V2 up to Vp minus 1 are the vectors, preceding vectors of Vp. So just we wrote Vp is equal to linear combination of preceding vectors. Okay, then let's go to next step. Let us consider an arbitrary element x in H such that, so here V means V equal to H. So let's take H is equal to x. Nothing will happen. Just see here. See, we wrote here H is equal to span of V1 V2 up to Vp. So we can write this one as A1 V1 plus A2 V2 so on up to AP Vp. That is nothing but linear combination. Span means linear combination of the vectors. So this only I wrote in next step. This is x. Instead of h I took x. X is equal to c1 v1 plus c2 v2 up to cp minus 1 vp minus 1 plus cp vp. c1 c2 cp minus cp, these all are the scalars. We may take c1 instead c or d1 or anything, p1 p2 p minus 1 or pp, like this. Here p1 p2 may be a scalars. Substitute 1 in 2. 1 into means in a previous step we got a Vp value. We wrote preceding vectors linear combination. So substitute Vp here. Then we get x is equal to c1 v1 plus c2 v2 plus up to so on cp minus 1 vp minus 1 plus cp. Vp means in previous step we got a1 v1 plus a2 v2 plus up to a p minus 1 vp minus 1. Just I separated c1 v1 c2 v2 up to cp minus 1 vp minus 1 cp minus 1 vp minus 1, then cp a1 v1 cp a1 v1 plus cp a2 v2 up to so on cp a p minus 1 vp minus 1. Okay, just see here it is c1 v1, here it is cp a1 v1. So we can take v1 as a common. In next step we did x is equal to c1 plus cp a1 taking v1 as a common. In the same c2 plus cp a2 into 2 v2 common up to so on c p minus 1 plus cp a p minus 1 into v p minus 1. This is 1 p minus 1. Okay, so we see this is a scalar, this is a scalar, this is a scalar, and v1 v2 vp minus 1, it is a vector. So it is a linear combination of the vectors v1 v2 up to vp minus 1. So we can write it as x is equal to span of v1 v2 up to vp minus 1. Yeah, can we? Yes, we can. It is a linear combination, it is of the form linear combination. So we can write absolutely as span of v1 v2 up to vp minus 1. We just now recall that span means it's a linear combination of scalars and vector. The equation is in the form of combination of scalars as well as vectors. So we can write it as a span of v1 v2 up to vp minus 1. Then see here, we wrote x equal to span of v1 v2 up to vp minus 1. It's a previous step. Observe, first we do x is equal to span of v1 v2 up to vp minus 1 comma vp. Just now I told that v is equal to a, v is equal to h is equal to x. Then we wrote instead of h, x. In starting step we took h is equal to span of v1 v2 up to vp minus 1 vp. So instead of h I took x here. X is equal to span of v1 v2 up to vp minus 1 vp. Then we wrote vector vp. So we wrote after next step we wrote vp is equal to linear combination of preceding vectors. So vp as combination of preceding vectors of v, and using vp we remove the vector vp. Using vp we removed vector vp from x. Though we removed vp, still v1 v2 up to vp minus 1 vector spans h. See here, starting we wrote x is equal to span of v1 v2 up to vp up to this one. Though we removed vp using its preceding vectors, then also x is equal to span of v1 v2 up to vp minus 1 we are getting. Using v1 v2 up to vp minus 1 we get a vector space x. So see, though we removed sim, that is s, set v1 v2 up to vp minus 1 vp, except vp means just remove vp, v1 v2 up to vp minus 1 still spans h. So using v1 v2 up to vp minus 1 also we get a vector space v. Hence it's proved that statement 1. See statement 1. Statement 1. If one of the vectors in S, say vk, is a linear combination of remaining vectors, it is a linear combination of remaining vectors in S, then set formed from S, then after set formed from S by removing vk still spans h. Here just we are proved that first we took s is equal to set up to vp. We wrote it as h is equal to span of set up to vp. Just we removed vp using vp, writing vp as a linear combination of preceding vectors. So we just removed vp from the set. Even though we removed vp, it still spans h, means it still gets vector space using up to vp minus 1. Okay, this is the first statement we have to prove. Then next statement, if h does not equal to 0, which means it is not a null set, it has at least a one vector, some subset of S is a basis for h. We have to show some subset of S, any subset of S is a basis for h. Okay, basis means it consists all or, let's see this. Let's see statement 2. Note, B is a basis of H. Let, just formula here, let B is a basis for H. In case B is a basis for H, which means H is equal to span of, H is a spanning set, span of set. B is a basis of H if B is linearly independent. If B consists linearly independent vectors, which means using V3 we cannot get, using V1 V2 we cannot get V3, using V1 we cannot get V2. All are independent vectors which does not depends on others. Okay, so B is a linearly independent first case. Second one, if in case H is equal to span of B1 B2 B3 up to BP, using the vectors in B, if we write it as a spanning set, we get H, then it is a basis. First linearly independent, then we need to get complete H. So we say these vectors is the basis of H. Suppose that S is a linearly independent, which means the set of vectors in a set SR does not depends on any preceding vectors. Then by definition S is a basis for H. See, Suppose that S is a linearly independent. First case, S is linearly independent, we are saying. Then by definition S is a basis for H. If we write S as a linearly independent and a spanning set, then it is a basis for H. Okay, first linearly independent, it is proved. Then we wrote H is equal to span of v1 v2 up to vp, which is a set S. So here we wrote H is equal to span of S. So S is a basis for H. See, first case, linearly independent, it is proved. Set S is equal to v1 v2 up to vp are linearly independent, which does not depend on each other. Then second case, we wrote H is equal to span of v1 v2 up to vp. So it is a set S. H is equal to span S, which means it here H is equal to span S and it is linearly independent. Set S is a linearly independent, then S is a basis for H. Okay, if in case we wrote S is a linearly independent and H is equal to span S, using S we get a H, then H is a basis for S is a basis for H. So let's see. Suppose that S is linearly dependent. If in case set S consists dependent vectors, like in case Vp, there Vp depends on complete preceding vectors. So like this, suppose that S is linearly dependent, then by the definition one vector in terms of other vectors, then we will get now new set S except Vp. If it is a linearly dependent, we write Vp is equal to linear combination of preceding vectors. Then while doing some equations, then we remove Vp from the set. S except Vp we get, it is a subset of S. Case 1, suppose that S except Vp, it is a subset, is linearly independent, then S except Vp is a basis for H. So here S except Vp, it is linearly independent, statement 1. Also we get X is equal to span of v1 v2 up to Vp minus 1. So we wrote set except Vp as a spanning set. Then in last steps we got X is equal to span of v1 v2 up to vp minus 1. Okay, this is a set except vp. So here we wrote set except vp as a span of S except vp equal to X. We are getting a complete vector space. Also this set is a linearly independent now. After removing vp we get a linearly independent set. Okay, it satisfied two conditions. It is linearly independent. Also using S except vp set spanning, we are getting a vector space X. So we say, absolutely we say S except vp is a basis for H, which means X is equal to H only. S set except vp is a basis for X. See then next. So here we wrote that is only, suppose that S except Vp is linearly independent. Also we wrote it as a spanning set. Then S except Vp is a basis for H. Absolutely we write. It satisfied two conditions, basis condition. So S except Vp is a basis for H. In case S set subset is a linearly independent. Suppose if subset is again dependent, then what we see the next step. Suppose S except Vp is linearly dependent. Linearly dependent means in case here in this set we have up to Vp minus 1. Suppose Vp minus 1 is equal to sum of preceding vectors. If we get Vp minus 1 vectors as a linear combination of preceding vectors, that is Vp minus 1 equal to, if in case we get V vector, last vector as a anything d1 v1 plus d2 v2. So here Vp minus 1 is depending on which vectors v1 and v2. So it is not a linearly independent vector, it is a dependent vector. So in case what we have to do, if we set we have dependent vectors. So to solve this we see. Suppose S except Vp is a linearly dependent, we know we can rewrite one vector in terms of other vectors, then we get a new set. So if in case Vp minus 1 is also a linearly dependent set, using some equations starting we did, we can remove vp minus 1 also, like we removed vp. Then we get again a new set. If in case in the set also we have vp minus 1, vp minus 2 is also linearly dependent, then using some steps we can remove vp minus 2 also. In the same way, at last we get a single vector, which means it will be linearly independent, confirmed, definitely. That is only error. We get linearly independent set at last. Once the set is linearly independent, then it becomes a basis for H. Once it is linearly independent, it becomes basis for H. So that is H except to 0, means except a null set. It is a basis for H. So we get a set like this. X is equal to span if all the vectors are linearly dependent. At last will remain only single vector v1. So it is a linearly independent first step over. Then we also wrote x is equal to span of v1. Second statement also proved. Hence v1 is the basis for x. We can write. This is the statement 2. Although the video may be good, please do like, share and subscribe the video. Signing out your school education friend NVK.